Okay, this is going to be the first video in two videos for section 6.4, which is working with Taylor series. Specifically, one of the new ideas we're going to be looking at is the binomial series. Let's go ahead and look at a function f of x, which is equal to 1 plus x to the r power, where r is a real number. If r is equal to 0, then 1 plus x to the 0 power is 1. If r is 1, 1 plus x to the first power is 1 plus x. If r is equal to 2, 1 plus x quantity squared is 1 plus 2x plus x squared. If r is equal to 3, 1 plus x to the third power is equal to 1 plus 3x plus 3x squared plus x cubed. R is equal to 4, 1 plus x to the fourth is equal to 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. The binomial coefficient on x to the n is the r choose n, or r factorial divided by n factorial, r minus n factorial. And so you probably would have seen the binomial theorem probably in pre-calculus a little bit, and maybe in Cal 1 as well. For a non-negative integer, so we're talking about 1 and 2 and 3 and 4, 1 and 2 and 3 and 4 and 5 and 6 and etc. Those are our non-negative integers. R, f of x, which is equal to 1 plus x to the r, can be written as the sum n equals 0 to r of r choose n, r choose n and then x to the n power. So let's do an example where we'll expand. I thought I fixed this here, so no f of x here. It's just we're going to expand 1 plus x to the sixth power. So 1 plus x to the sixth power is equal to the sum n equals 0 to 6 of 6 choose n x to the n, which is equal to 6 choose 0 x to the 0 plus 6 choose 1 x to the first, all the way out to 6 choose 6 x to the 6. If we go ahead and write those, that's going to be the first one, 6 choose 0 will be 6 factorial over 0 factorial times 6 factorial. 6 factorials will absorb, and 0 factorial is defined to be 1, so we just have 1. And then we have 6 factorial over 1 times 5 factorial. So I'll just write out 6 factorial, 6 times 5 factorial, and then you had a 5 factorial in the denominator, so we just have 6 factorial. The next one is 6 factorial over 2 factorial, 4 factorial. So write the 6 factorial, 6 times 5 times 4 factorial, all over 2 factorial, 4 factorial. So the 4 factorials absorb. 2 factorial is just 2 times 1. So 2 goes into 6 3 times. 3 times 5 is 15. So that goes with the x squared. Okay, and then the cubed term, we have 6 factorial, which we can write as 6 times 5 times 4 times 3 factorial, over 3 factorial, 3 factorial. So the 3 factorials will absorb. 3 factorial is 3 times 2 times 1, which is 6. So the 6's will absorb, and we say have 5 times 4, which is 20. And then the rest of the terms, the coefficients specifically, are going to be similar to the first three terms. So these three coefficients here are going to be very similar in working out as the latter three. Okay? All right. So let's go ahead and look at, this is the case for a non-negative integer. And on the next slide, we're going to look at things that are not non-negative integers. Okay, so any real number, so basically this is excluding the counting numbers 1, 2, 3, 4, etc. So if we have f of x is equal to 1 plus x to the r, we're going to do a Taylor series centered at 0, or Maclaurin series. F of 0 is going to be 1. The first derivative of this function is going to be r, 1 plus x to the r minus 1. So the first derivative evaluated at 0 is r. Second derivative is going to be r minus 1, 1 plus x to the r minus 2. Evaluate the second derivative at 0, we have r minus 1. Third derivative, and then third derivative evaluated at 0. Maybe you start noticing a pattern. So this is the third derivative, and this is r minus 2. So it's going to follow that pattern all the way out to taking the nth derivative, and so we would have not quite n here, we'd have n plus 1. Kind of like here we have, think of this as minus 3 plus 1 there. Okay, so minus 3 plus 1 there. This is your n here because of the third derivative. Okay. So when we're looking at our binomial coefficients, these are our Taylor coefficients. C sub n is equal to the nth derivative evaluated at 0 all over n factorial. So here's your nth derivative right there. Okay. And for any real number r, we're going to define r choose n to be exactly the nth derivative evaluated at 0 over n factorial here. So that's how we're going to define it. Okay. Alrighty, so let's go ahead and we're going to look on to looking at the binomial series. So the binomial series for f of x is equal to 1 plus x to the r power is going to be equal to the sum n equals 0 to infinity r choose n x to the n, which is equal to 1 plus rx plus r minus 1 over 2 factorial x squared, all the way out to the nth term, which is r minus 1, r minus 2, r minus 3, all the way out to r minus n plus 1, all over n factorial x to the n, and then that continues. Probably one of our favorite tests for determining the interval of convergence is the ratio test. So we're going to apply the ratio test. So we're going to go to the nth plus 1 derivative. So this is always going to be 1 less than that, so that's going to be n. Okay. And we have n plus 1 factorial. And then we already went ahead and divided by a sub n and took the reciprocal of that. So you're going to have the n factorial over the n plus 1 factorial, which we'll write as n plus 1 times n factorial, so we're left with an n plus 1 in the denominator. Okay. And pretty much everything will absorb except for this r minus n in absolute value, and then also we have x to the n and x to the n plus 1, x to the n plus 1 in the numerator, x to the n in the denominator, so we're left with an x to the n in x, just an x in the numerator, absolute value. The n is what's moving, so quotient of the leading coefficients, it's going to be 1 over 1, so the limit here is going to be x. And we're going to have convergence by the ratio test provided that this limit of absolute value of x is less than 1. So this gives us an interval of convergence of negative 1 to 1. The convergence at the endpoints is going to be dependent on the value of r. Okay. So we're going to work out, I think, 3 examples, 2 of them dealing with the same Maclaurin series, and then one other Maclaurin series example. Okay, so we're going to be looking at finding the Maclaurin series for f of x is equal to the cube root of 1 plus x. So what we want to do is we want to make this look like 1 plus x to the r power, so we're going to have to do some manipulation here. I'm going to go ahead and factor out a 1,000, and so what I have is 1 plus x over 1,000. Okay, so I have 1,000 times 1 plus x over 1,000, that whole thing to the 1/3 power, that's what the cube root is. Then using properties of exponents, this is a 1,000 to the 1/3 power plus x over 1,000, and then that's raised to the 1/3 power. Okay, now 1,000 to the 1/3 power is the same thing as the cube root of 1,000, which is 10, and then we have 1 plus x over 1,000 to the 1/3 power. And so this is now our 1 plus x to the r. And so it's going to follow the pattern. Okay, so this is going to be equal to 10 plus, well, I'm going to factor out the 10, so it'll be 1 plus, and then it's going to be r, which is 1/3, and then what your x is, in this case it's x over 1,000. Okay, and the next term is going to be r, and then r minus 1, so 1/3 minus 1 is minus 2/3, and then your x to the second power, which is going to be x over 1,000 squared, all over 2 factorial. Okay, And then we'll do it for the next one. R minus 1, r minus 2, and then your x to the third power over 3 factorial. We'll do a couple more just to kind of get the feel for this. So here's your r minus 1, r minus 2, r minus 3, and then your x to the fourth power, all over the 4 factorial, and maybe one more. So r minus 1, r minus 2, r minus 3, r minus 4, and then your x, which is x over 1,000 to the fifth power, all over 5 factorial, and then this pattern is going to continue. Okay, we'll close our parentheses here. All right, and let's see what we got going on. So we have 10, and then it's 1 plus x over, and what we're going to do is we're just going to try to rewrite this. So x to the first power, we have 1,000, when you can write that as 10 cubed, and then times 3, so here's that 3 right there. Okay. All right, now the next one, we have the 1 times negative 2, which is going to be negative 2, x squared, and then the 1,000 again, we're just going to write it, so this is going to be 1,000 squared, or 10 to the 6. Okay, then we got 3 times 3, which will be 3 squared, and then 2 factorial. So we're trying to write it so if we can notice some patterns, and maybe we can come up with a series representation of this. Okay, all right, now the next one, 1 times 2 times 5, and that's a 1 times a negative 2 times a negative 5. So it's going to ultimately be positive. So 2 times 5, x cubed, and then we have 1,000 cubed, so that's going to be 10 to the 9th. And we have 3 times 3 times 3, which is 3 cubed, and then 3 factorial. Okay, next one we're going to look 1 times negative 2 times negative 5 times negative 8, so ultimately that's going to be a negative. So 2 times 5 times 8, x to the fourth, okay? And then we have 1,000 to the fourth, which will be 10 to the 12th. And then we have 3 times 3 times 3 times 3, that's going to be 3 to the fourth. Okay, and then 4 factorial in the denominator. And one more, let's see. 1 times negative 2 times negative 5 times negative 8 times negative 11. So that's 4 negatives, so that ultimately makes that a positive. So 2 times 5 times 8 times 11, x to the fifth. 1,000 to the fifth power is going to be 10 to the 15th power. And then we have 1, 2, 3, 4, 3, how many? Hold on, 1, 2, 3, 4, 5, sorry. So we got 3 to the fifth. And then 5 factorial. And then that pattern is going to continue. And so we're going to see if we could write this as a nice series. Maybe we can find a pattern for it. So we're going to go ahead and just rewrite what we just wrote down there. And we'll see if we can notice some patterns here. Okay. So the patterns for the x the first, x squared, or even here, x to the 0, x the first, x squared, so we got a pattern going on there. It looks like after the first 2 terms we begin doing an alternation in signs, which may mean that we would have to neglect the first term or maybe the first 2 terms. And then we kind of have something going on. We have a 1, and then a 1 times 2, and then a 1 times 2 times 5, and then a 1 times 2 times 5 times 8, and a 1 times 2 times 5 times 8 times 11. So we're probably going to have to chop off the 1 so that we have a nice pattern of plus 3. Okay, so if we do that, that's going to neglect the first 2 terms being written in our series. So I think we're going to do that. And then we got good patterns here, increasing on the 10s, the exponent by 3. And then the 3 squared, 3 cubed, 3 to the 4th, those are nice pattern, and the factorials are all nice pattern. So I think in order to get this to fit this pattern here, we're going to have to neglect the first two terms. We're going to have to leave them out. So let's see what we can do about that. Okay, so we're going to leave the first two terms out. So 1 plus x over, and we can say 3,000, or we can write it as 10 cubed times 3, doesn't matter. Okay, plus the sum, and I'm going to go ahead and start it at n equals 2, just so the exponent matches up. Exponent on the x and the 3 is 2. And also the factorial would be a 2 factorial. So we want the first term to be negative, so if we do negative 1 to the n, that would be a positive 1, so we want it to be negative, so we'll do negative 1 to the n plus 1. Okay, and then we got to do that weird pattern of 2 times 5 times 8, so we'll do 2 times 5 times 8. And so we want the first term to be 2, and then we want to increase by 3, so we want a 3n, and so if we're going to do 3 times 2, we'll figure out what we need to add or subtract here, and we want that to be a 2 there. So that would be, let's see, x would be equal to minus 4 there, so we would want to do a 3n minus 4 to describe that pattern. All right, let's get this out of the way. So 3n minus 4, x the n, 10 to the, and then we want to increase by 3, so 3n, 3 to the n, and then n factorial. Okay, and so we have written this as an infinite series. Sometimes this happens where the first term or two is neglected, and I don't mean neglect, but I mean we can't include it nicely in the formula. Maybe there's another way, I'm just not familiar with it, but I haven't seen a way of incorporating those two in real well, unless you're just using the R choose N notation. So you can do it with using the R choose N notation. Anyways, but I like to write it out a little more explicitly. So this is more explicitly than using the R choose N notation. Okay, so we're going to use this series here in the next problem. So we're going to estimate the cube root of 1001 using that binomial series that we just came up with, and we want to be accurate up to 3 decimal places. So we actually figured out what the 5th degree Taylor polynomial centered at 0 was, or the Maclaurin polynomial, the 5th order. So let's go ahead and rewrite that there, and we're going to go ahead and use this as an estimate for 1001. So what value do we need to plug in here for x? That would be 1. So we're going to plug 1 into our polynomial. Okay, so we'll plug that in, and then we'll put this into our calculator. So we're going to use a polynomial to estimate a cube root here. And if our result is not accurate enough, just use a larger polynomial, a little bit of guess and check going on. Okay, so putting that into our calculator, we get 10.00333222283 blah blah blah. Just a bunch of them. Now if I also do the cube root of 1001 in my calculator, that's going to be 10.0033, looking good so far, 3222839, oh, and finally we're off at that whatever decimal place that is, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, so we're accurate to 12 decimal places, so we've certainly met the expectation of the problem of 3 decimal places. Okay, so maybe we could have gotten away with a smaller order polynomial, but I just chose to do the 5th order polynomial since we had already found it. Okay, let's do one more example where we find the Maclaurin series for a polynomial, not a polynomial, for I guess it's a radical. We'll take a look at it. I don't know the best way to describe it. It's a reciprocal of a cube root function, I suppose. Find the Maclaurin series for f of x is equal to 1 over the cube root of 1 plus x squared. So we need to rewrite this to get it into the binomial form. So it's going to be 1 plus x squared to the minus 1/3 power. And so the binomial series goes 1 plus rx, and in this case the r is minus 1/3, and instead of x we have x squared, so x squared plus r, and then r minus 1, and then your x, which is x squared in this case, over 2 to the second power, and then over 2 factorial, plus r minus 1, r minus 2, and then your x squared to the third power, all over 3 factorial, plus r minus 1, r minus 2, r minus 3, x squared to the fourth power, all over 4 factorial, and maybe we'll write out one more, r minus 1, r minus 2, r minus 3, r minus 4, x squared to the fifth, all over 5 factorial, and that pattern is going to continue, and we're going to see if we can come up with a pattern here. So this is going to be 1 minus x squared over 3 plus 4x to the fourth over 2 factorial, and also we have a 3 times 3, so that gives us a 3 squared. And the next term is negative 4 times 7. So I'm not multiplying it out because I'm trying to notice what the pattern is. X to the 6 over 3 cubed times 3 factorial plus 4 times 7 times 10 x to the 8th divided by 3 to the 4th, 4 factorial, minus 4 times 7 times 10 times 13 x to the 10th, and I guess I could have put the times 1 in front of these other ones here also, and I can notice that pattern of 1 times 4, 1 times 4 times 7, 1 times 4 times 7 times 10, and you see an increase by 3. Now this is supposed to be a 13. I don't know where the 17 came from. Sometimes we get carried away in the excitement. Okay, and that's going to all be over 3 to the 5th, 5 factorial, and that's going to keep going. All right, now to fit the 1 times 4, 1 times 4 times 7 times 10, etc., I think we're going to have to leave out the first 2 terms, or possibly we can... oh wait, this does fit the pattern. So here's our 1 times 4, 1 times 4 times 7, 1 times 4 times 7 times 10, 1 times 4 times 7 times 10 times 13. So I suppose we're okay, and we just need to exclude the 1 at the very front there. Okay? I think we'll start off at 1. Okay? And we're going to do negative 1 to the n. We'll put that at the end. But we do have the pattern 1 times 4 times 7 times ... And we're increasing by 3, so we want 3n and then something. When n is equal to 1, we want that to be equal to 1. So I think we'll want to do a 3n minus 2 will satisfy this. Let's go ahead and do a 3n minus 2, and then we'll put the negative 1. And let's see, we'll want the first term to be negative, so negative 1 to the n will do it. X to the 2n, we want 2, 4, 6, 8, 10, etc. for the exponents there, divided by 3 to the n and n factorial, and that is our Maclaurin series for this particular polynomial. And that'll be it for this video. Stay tuned for the next one. I think this one will be on the longer side of the 2 videos.